Hey everyone, we're going live in period one for Honors Algebra 2. This is rational functions and their graphs. Rational functions and their graphs is kind of a piggyback onto what we've been doing. So we've been simplifying rational expressions, and we've also been solving rational expressions in class. The simplifying part is the big one that really helps us determine, where our graph's going to go and what it's going to look like. But a lot of the things that we do simplify have names in math. And one of the big names that you're going to hear is something called an asymptote. The next big name that you'll hear of is something called a hole. So in order to analyze a function, determine the equation of the asymptote, hole, and intercepts, we have to understand what the behavior is going to do and how to go about it. Anytime you have a hole, it's because you've factored something completely out from the numerator and denominator. So say, for example, you have x on top and x on bottom. You factor that out. That's what you would create as a hole in your graph. And I'll show you what an example of that looks like here in a second. An asymptote is where you would draw an imaginary vertical line, essentially where your denominator equals 0. So anytime that you have a factor in your denominator that equals 0, that's where you would create something called an asymptote. It's just a line that your graph cannot touch because of the fact that if you have that number, it'll create 0 in your denominator, which is undefined. So here's a good example for you to put from your notes on what a vertical asymptote would look like. So say, for instance, x is equal to a number. Anywhere the denominator is equal to 0, your graph cannot cross a vertical asymptote. So a super simple example, x plus 2 divided by x minus 3. If I were to look for where you would have essentially a domain restriction, okay, that keyword domain restriction, you could not put 3 into your denominator. When you go to graph, you will have to take and put a dashed line where 3 is located. That dashed vertical line will symbolize a line that you cannot go across. Your graph will approach that line, but it will never cross over it, meaning that you will have something that looks like it's going to touch, but it will never actually quite touch. It may come up from the top, or go up from the top and then come up from the bottom, or vice versa. But what you'll have to do is find that asymptote and then plot like 2 or 3 points to the left of it and 2 or 3 points to the right of it to see how the graph interacts. And I'll show you what that looks like whenever we do our first example. On the flip side, a hole. A hole is where the numerator and denominator simply cancel out, creating a hole in your graph. So in the next example that I show you, you've got x plus 2 over x plus 2 times x minus 3. You've got x plus 2 that cancels out, so there's a hole at negative 2. And then that x minus 3 still in your denominator creates that vertical asymptote. So as you can see there, the vertical asymptote is definitely still at 3. The only difference between a vertical asymptote and a hole is that you can still draw your graph, just that where you will have a hole literally in your graph at that specific point. The vertical asymptote will basically kind of make your graph go completely one way or the other. The hole does not stop your graph, it simply just creates a hole. Since we are in class, I'll give you another minute if you're copying this down. Does anyone in class need more time? All right, let's go to the next thing. So using a table of values, we can find the integer values or friendly points of a function near any vertical asymptote on both sides of the asymptote. So as I talked to you before, you'll be plotting 2 to 3 points on either side of the asymptote in order to determine where your graph is, and based on that, you'll be able to determine where your lines are going. So that's what we call a vertical asymptote. On the other side of things, we have 2 other types of asymptotes. The first one is called a horizontal asymptote. So horizontal asymptotes create a horizontal line. This, in certain situations, you can cross. As we get into the lessons, there is an example in which I'll show you that it can cross. But there's 2 ways to determine if you have a horizontal asymptote. And pretty much all of these will, at some form, have some type of horizontal asymptote. The first way is the small to big method. You're looking for the lead exponents. If the lead exponent on top is smaller than the lead exponent on the bottom, then your horizontal asymptote is at y is equal to 0. That's way number 1. So horizontal asymptote, I call it the small to big method, where your smaller exponent is on top, your bigger exponent is on the bottom, so your horizontal asymptote is always at y is equal to 0. So if your lead exponent on top is 1 and your bottom one is 2 or 3 or 4 or 5 or whatever, it's always at y is equal to 0. The next method is called the sames method. I made this up, so the names are weird. Same exponent on top and the same exponent on bottom means that your horizontal asymptote will be y is equal to your lead coefficients. So you'll have a horizontal asymptote or a horizontal line that can be crossed sometimes, but not necessarily always the case. So if you've got 2x plus 1 over 3x minus 1, they both have an exponent on their x that's 1. So your lead coefficients of 2/3, y is equal to 2/3 is where your horizontal asymptote is going to be located. So recap, vertical asymptotes, all based on your denominator. Holes are where you cancel things out. Horizontal, if it's small over big, your horizontal asymptote is y is equal to 0. If they're the same, it's your lead coefficients. The last thing is, what if you have a big over small? If you have a big exponent over a smaller exponent, you have something called an oblique or slant asymptote. I call it the big to small method. So, in the example given, you have x squared minus x plus 3 over x minus 1. The x squared is bigger than the x. So then you have to use synthetic or long division to find a slant asymptote. That's why we learn how to do synthetic or long division. The way it works is you only look for what you've got synthetically divided. Your remainder does not matter. You can ignore your remainder. And then you draw that line as a dashed imaginary line in which your graph will not cross. Two things to point out. Number 1, you can have a slant asymptote and a vertical asymptote. Number 2, you can have a horizontal asymptote and a vertical asymptote. Number 3, you will never have a you will never have a horizontal asymptote and a slant asymptote at the same time. I'm recording, just so you know.
Okay.
So
I was going to ask, we're supposed to leave everything in factor form.
yes. Yeah. Okay, so You'll never have a horizontal asymptote and a slant asymptote, just because it all depends on the exponents. Does anyone need more time? Okay. All right. So I'm going to go through example number 1 with you, and then that'll be it for this video. And then we can continue on Monday, and I can make more videos for this as well. Here's example number 1. Find the domain of each rational function. Completely graph each function. So first thing I'm going to do is I'm going to look to factor my denominator. When I factor my denominator, I'm going to get x minus 3 times x plus 2. That means in this case, for my domain's sake, x cannot be equal to 3 or negative 2. This makes my domain negative infinity to negative 2, negative 2 to 3, and then 3 to infinity. By factoring this, I'm going to go down through each step for you just to kind of show you what I'm looking at. First thing is, do I have any holes? I do. I have a hole at 3. So wherever my graph is that x is equal to 3, I will have a hole. And I'll get to in a minute how to find that, because these will cancel. I will have a vertical asymptote where x is equal to negative 2. I will have a horizontal asymptote. I'm recording, just so you know. Can it wait like 5 minutes? Okay. If it's about factored form, you can leave it in factored form. Okay. I have a horizontal asymptote. If you take a look, I'm going to do this one in red. If you take a look at this is 1 and this is 2, because I have the small to big, my horizontal asymptote is y is equal to 0. So except for my hole, I'm going to go ahead and I'm going to put all of these on here. I'm going to draw an imaginary line at y is equal to 0. Because I have a horizontal asymptote, I don't have to worry about a slant. And then where x is equal to negative 2. I'm going to make a t-chart for my equation. My equation being x, y, 1 over x plus 2, because that's what it's simplified down into. I have my vertical asymptote at negative 2, where it's undefined. I'm just going to look and see if I can plug in some numbers that are kind of close to that undefined, so I can get a general idea of whether my graph is going to look something like this, or if it's going to look something like this. And usually 2 to 3 points will do it. It's up to you as to if you want to do more than 2. So negative 1 and 0, if I plug those in, I end up with 1 over 1 and then 1 over 2. So I'm recording right now, so can you wait 5 minutes? Yeah, give me 5 minutes and then I'll answer your questions about the exam. So go ahead, so negative 1, 1, and then 0, 1/2. So right here, this this graph is going to look like this. Now I'm going to have a hole somewhere around 3. So where 3 is. And then go through. I'll show you how to find that point exact in a minute. And then just to double check, -3 and -4. When I plug that in, I'll get -1, and then I'll get 1 over -2. So down here, -1 and 1/2, and then I'll have another line that goes like this. They'll always curve around those asymptotes, especially in this case. Horizontal you can sometimes cross, but in this case you won't. There's a specific type in which you break up into 3 or 4 different pieces. I'll show you that later on. How to find where your hole is going to be specifically, you just plug 3 in. You end up getting 1/5. So at approximately 3, 1/5 is where you're going to put that hole. That looks pretty good from there, but that would be your graph. All right, we'll finish up the video next time.